Well, first, thank all of y'all for coming today to hear my comments. I really am honored to present this lecture on AIST's behalf in honor of the Adolf Martens lecture. Having taught mechanical metallurgy for some 40-odd years, I chose the subject of mechanical properties. And so the title is Enhancing Fatigue Performance of Steels, and I added a little caveat and other alloys. Have we learned anything from the past? And I hope to take you through a little bit of a history, but also bring a few of you up to speed and show you some examples of some things that are happening today. A few brief comments about Adolf Martens. I think he's made many contributions to metallurgical materials engineering. Certainly Julie commented on a few of those this morning. He's most known, and I think most of us would recognize his name, as related to martensite, a very characteristic microstructural feature shown here for plate martensite, taking one of my colleague George Krause's papers, of a very distinct feature. He didn't give it the name martensite. That came later when it was provided along by Osmond in 1895. But the lecture today is on mechanical properties, and he did much more than work on martensite. He makes significant advances in the areas of physical and mechanical testing. For example, in 1880, he developed an oblique microscope that allowed him to replace hand drawings with photographs to record microstructural images. The lower left image shows one of his sketches of a micrograph, and the right is a schematic drawing of the oblique microscope that allowed him to record images directly on the photographic film. You look through his career, and from the 1870s to the early 1900s, he was involved with several institutes in Germany, involved with everything from railroads to mechanical testing, and it's through those activities that he developed many test methods, only 3 of which I've illustrated here. Experimental method to measure scratch properties or resistance to surface, Burnell hardness, mechanical testing. Julie mentioned the comments about worrying about properties from one laboratory being the same at the other. So it's really this part of his career that I've attached my lecture on mechanical properties. So I think it is appropriate to talk about mechanical properties. So I chose this title. Have we learned anything from the past? And so let me give you a few slides to sort of illustrate why I came up with that. Well, the place to start is, what's the past? And so in the area of fatigue really started formally in terms of studies in the early 1800s, really with railroad axle failures and other failures of components of such things as mining equipment, chains, other equipment for operations. 1830s, French engineers described the phenomena of fatigue, railroad axles and mine equipment. Scientific research originated in England in the 1840s. And then Wörler came along and really did the first fundamental investigations in Germany in the 1850s to 1870s. And so what's shown at the bottom is a sketch of one of the classic failures of a railroad axle, showing you the failure that occurred at a discontinuity or transition in diameter, and a corresponding the fracture surface. And certainly, as we recognize, railroads are parts that are cyclically loaded just by the nature of their operation. And so at that time, what did we learn? From the 1800s, what did we know? From the work of Wörler, Martens followed Wörler's work at the institutes and did work on fatigue, but what did we know? We learned the importance of stress amplitude. We learned the importance of mean stress. We certainly learned the importance of stress concentration. All of that provided design guidelines for new components. Design criteria came out at that time. Design criteria, such things as in a cyclic loaded sample, the maximum stress can't be greater than the strength of the material. So correspondingly, work came out that there was a maximum allowable amplitudes that you could apply. So the fatigue properties were simultaneously controlled by both amplitude and peak load. Test methods evolved. Wörler developed a rotating bending fatigue machine to assess the properties of materials and to systematically assess variations in alloying and development in terms of performance. Same time, but there was the basics of failure analysis evolved. Wörler has Martens had a very interesting paper in the late 1800s on failure analysis. And with respect to fatigue, a few things came out. Fatigue cracks propagate perpendicular to the maximum tensile stress. So they tend to plot out for you a map of the stress state through the material. That's what we knew in the 1840s. So let's jump ahead. Railroad axle failure, 2004. Fatigue fracture originated at a surface profile irregularity likely introduced during axle reconditioning. If you look at the lower left-hand image, it looks exactly like the schematic from 1844. And on the right-hand side is the flat fracture of fatigue having nucleated at the top and grown throughout the cross-section. So that's pretty good, so let's move forward. So here's railroad axle failure 2010. The axle failed in fatigue near the midpoint of the axle body. And so these are both from reports of the Canadian Railway Institute. And so here are examples of what I mean by a concern of, have we learned anything from the past? Well, what kind of literature do you go to learn about fatigue failures? Well, I seek that very important scientific document, the Denver Post. And so you can go to most any literature, news, and learn something about fatigue failures in materials. And so let me show you a couple of examples, and I could fill the rest of the day about examples of fatigue failures, but one of the problems with fatigue failures is when they occur, they are often very catastrophic. And a catastrophic failure then leads to serious problems that we'd like to mitigate. Here, fatigue causes failure of Delta accident. Delta Airlines inspecting 727s for fatigue problems. Well, one of the classic failures we all learned about in early mechanical metallurgy was the de Havilland Comet in the early 1950s, in which the British airplane came along as one of the first planes to really move into jet-operated commercial air traffic. They had two catastrophic failures in 1954 that led to them putting down the whole fleet and redesigning. It also set back the industry in Britain significantly in terms of development of new aircraft. That was at the time that Boeing was beginning their development for 707s, and so this was a really big transition worldwide in terms of where the supremacy was going to be. But what came out of that was the need to do tests, not just simple design tests, but full pressurization tests. And so the figure on the left shows a picture taken where it shows the airplane, an exemplar one, being pressurized in a container, cyclically loaded, and the lower right hand shows the crack at a port which developed due to the cyclic loading. And so we learned the importance of cyclic loading an aircraft from pressurization tests. That led to the modern design concepts and testing that we use today. Having known that, let's move on to another issue. Here's Aloha Airlines 34 years later that failed because of cyclically loading pressurization tests in a situation where an airplane flew many more cycles of takeoff and landing than are normally anticipated. So the NTSB report said the probable cause of this accident was fatigue damage of the fuselage skin. I show this because this is particularly shows you how fatigue can become very close to home. My mom and dad were in Hawaii at the time that this accident occurred, and they were on that airplane 6 days before this photograph was taken. For those of you that understand fatigue, think where mom and dad were compared to this image. Because they were there, and the reason you know that is each of those airplanes has a name, Queen so-and-so or King so-and-so, and Mom had remembered that, and she sent me all the stuff from the Honolulu newspaper. So it can be a home. But the consequence of fatigue can lead to other things. Compared to our previous talk, this is a comment on traditional energy storage, which is jet fuel fire. These are the fuel farm fire that occurred at Stapleton in the early 1900s, the 1990s. And the fire that you just saw, the probe blames 4 small bolts for the airport fire. That was 2 million gallons of jet fuel, shut down Stapleton for a few days, and friction heat from the damaged coupler ignited the fuel. Well, let's look at a couple of pictures. Upper left is the fuel farm after the fire was over with. On the lower right, middle on the right-hand side shows a motor with a pump, and on the lower left is a bolt and a fractured bolt, and the purpose of those bolts was to hold that pump motor to the foundation. During operation, the bolts broke. The pump was allowed to displace. A consequence of the displace, the pump misaligned, caused friction, generated heat, and led to what you see there. So the conclusion that came found from the NTSB is fracture surfaces of 3 of the bolts indicated fatigue cracks, initiating at multiple sites along the thread roots on diametrically opposite sides of the bolt. The reason I show this is simply a bolt, yet the catastrophic consequence was what you saw. Yet the failure is a fatigue. And so we really, and I'll end up with some closing comments about bringing all these together.